And now they're arguing, which is funny. Okay.
Okay, so thanks again for joining us. This is the Boston HPC and Meetup group. Today we have Natasha, who's going to be speaking about HPC monitoring. She had an internship at a national lab. Well, there's always an interruption between dogs and roofers. Anyway, sorry, take it away.
Okay. Yes, my name's Natasha, and let me give you, sorry, we're just changing slides here. A bit of an agenda today. So I'll start with talking a little bit about monitoring an HPC system and what that means. Then we'll go into bottleneck analysis, and then I'll talk about my project at Los Alamos. So traditionally, we think of a computer in terms of 4 basic units. We see the CPU as having a bus that connects memory, storage, and I/O. So to monitor a system like this, that essentially means that we are looking at various components of these 3 big items and finding a way of what the latency is, what kind of bandwidth issues that they run into. So the issue with monitoring an HPC system is that there are many of these different types of components. You have CPUs, multiple CPUs, thousands, millions. You have memory units, you have storage, and interconnect. But you also see that there's sort of similarities between the traditional PC system along with this HPC system. We have the same sort of memory blocks, same CPU, same storage, maybe just in a different architectures, different performance metrics. So let me start first by talking a bit about Trinity, the supercomputer at Los Alamos National Labs. So as of June 2020, it is currently the 11th top supercomputer in the world, and top in terms of floating point operations per second. So about, I think in November 2019, Summit was #1, ranked #1. And recently, Japan finished building their Fugaku supercomputer, so now that is rank 1. This slide is a high-level architecture of Trinity, which is taken from the Trinity website itself, not something I designed. But here you get kind of the basic idea of all the different components. So it has login nodes on the left in orange that connect to the compute nodes on the top here. They have about 9,500 Haswell, 9,500 Xeon Phi, Intel cores. And then there's also about 2 petabytes of total memory, that's RAM memory, and then different specific, HPC specific computer components. So there's gateways, there's the Lustre file system, which is its own parallel file system that has routers that connect the entire infrastructure. There's the burst buffer. And then we have as well these other separate file systems on the bottom here. And there's different file systems that connect for different purposes. There's XFS, NFS, and Lustre is probably the most important file system, which allows 2 users to update different files at the same time. So that allows for different cores to do that at the same time, and so on and so forth, different applications. So one question is, how would you go about monitoring this kind of system? And the current idea is that you gather lots of data. Now, I say that like as a blanket statement, but there are teams at Los Alamos that do this. There's entire infrastructure that is well thought out, well designed, but the idea is that you gather data. And I have a quiz for people here. Let's see how much monitoring data is collected on Trinity. What do you guys think? You can feel free to do it in the chat or whatever.
I'm going to say gigabyte a second.
Okay, sweet. A little bit higher.
Higher.
A little bit higher. It turns out to be around the order of 5 terabytes per second, which is an insane amount of data.
Wow.
That is obviously not in one storage unit, but it is distributed across many different units. And that is an immense amount of data to collect. And the question is, how do you manipulate it, and how do you find what's useful out of all that data? So I will talk a little bit about the typical monitoring ecosystem. This is not what LANL uses. They use other techniques. I think there's more data. There's definitely stuff online about it. I should have looked this up, but I didn't exactly figure out what they did for this. But in Red Hat, what we did was they had something called Prometheus, which gathers data, and that collects a stream of metrics. So Prometheus is an API that looks at CPU usage. It looks at different types of I/O weights, interrupts, system calls. It gathers all this data and finds a place to store it. And an example storage here is Ceph. Ceph is an object-oriented storage. So it basically stores these time series data. And once you've stored, let's say 5 terabytes of data, you want to find a way to provide meaning to what that data is. And usually that's in terms of, let's say, alerting, or let's say if I pass a certain threshold, certain emails are sent out or whatever to alert people of potential issues. And there's also visualization, which Grafana is a good example of that. Grafana uses basically a dashboard format to show what are the different metrics, and so you can visually see that. There's also machine learning techniques that have been developed recently, and I worked a little bit on that at Red Hat, and they use a lot of time series sort of techniques to figure out where there are threshold issues, as well as many different sort of statistical anomalies, let's say. So let's take a little bit of a step back and talk about bottleneck analysis. And what you typically see in a classic HPC course is the roofline model. Roofline model basically looks at computational intensity versus the attainable floating point operations that you hope to achieve per second. And computational intensity can basically be thought of as how many operations per byte of data. So for example, let's say you're doing addition. You take from memory 2 bytes of data, the two bytes, maybe 8 bytes of data, whatever for each. But basically, in order of 1 byte, and you apply one addition, one operation on those. So it's basically a 2-to-1 ratio, or a computational intensity of about 0.5. You can argue for different floating point units is different around some sort of fraction, and that would basically happen to be typically an I/O bottleneck system, where you end up being on the lower end of this computational intensity x-axis. I don't know if you can see my mouse, but basically around this area where you have I/O bandwidth issues, where you're bound by the amount of I/O you can get from your memory device. This computational roof is the total floating point operations that you're able to calculate or able to attain for the hardware that you're given. So a CPU. If you max out your CPU with peak power, everything, what is the computational roof that you have for that? So with this framework, a question is, okay, what does it mean to be compute bound, and what does it mean to be I/O bound? So more specifically, you can ask, well, is this compute bound in terms of the number of processes that are happening on the system? Have I maxed out on the available resources because other processes or applications are occurring or are working on the same system as I am? Another thing that you can look at for I/O is looking at network packet loss, page faults, time that's taken for file system traversal. So these are sort of ways that you dig deeper into see, okay, what exactly is my compute bound application, or what exactly is my IO bound issue. So we can kind of look at this roofline model as a multi-dimensional optimization problem, so to speak, where instead of having like a typical XY axis, you can think of this as XY axis being the same as a roofline model, but there's sort of additional parameters to take into account. So one additional, if you look at your surface, one additional constraint is network bandwidth. So that is a different basically surface that you can constrain your problem by. You can also think of context switches as being an IO bound issue that is an additional surface on this optimization plane. So adding all the different types of different bottlenecks that you can come up with can basically create a more well-defined space that can tell you what exactly is your bound on. So here's an example of a few techniques that we used this summer at Los Alamos National Labs. And they are basic. They are what you are used to using for a Linux system. So I'll give you just an overview of these. Top, I hope many people here are familiar with, number of processes that are happening and the bandwidth or the percentage of compute that they're taking. IO stat measures the read and write to the IO per second. There's VM stat, which looks at virtual memory, how much is available and how much is actually being used. And then there's the -D option for that, which shows you device-specific statistics. That is looking at, which partition of RAM that we're looking at. And then netstat looks at interfaces. So, or this -I looks at interfaces. There's other types of netstat commands that are useful. And then npstat is CPU usage. So let me see if I can share this screen and just show you a few. Can you see my terminal?
Yep.
Great. So if we look at top, this is your user can see that it has different commands. Right now I'm using Docker, for example. That is a standard one. Let's look at netstat-I. So netstat basically looks at the different interfaces, network interfaces on your computer. So for example, I have ETH0 and the loopback interface, and it shows you how many packets are sent, how many packets are received, and then other like flag issues that you can kind of look up in a table to see if you have specific network issues. Another one that's useful is vmstat, and it shows you the amount of swap memory, free, cache, so on and so forth. So these are the basic building blocks to figure out what is the potential bottleneck of your system and what could be a good way to, let's say, figure out how to fix them. All right, let me go back. Okay, moving on. I'm assuming you can see the screen.
Yep, go ahead.
I'll talk about my project at Los Alamos National Labs.
Can we pause maybe for, there were a couple of questions in the chat about the Trinity monitoring. You had a statistic of 5 terabytes per second of metrics. Is that gathered and stored 5 terabytes per second?
Gathered and stored. I'm not sure for how long. That is a good question, actually, whether or not they are being stored for forever, but at least they go through a storage system, yes.
Okay, that seems to have impressed the crowd here. That's a pretty impressive statistic. Thank you.
Mm-hmm.
And one other question: you had shown a multi-dimensional roofline analysis. Is there a commonly accepted term for the multidimensional?
This
Roofline?
is kind of just a framework that I've thought about, other people have thought about. I don't think there is a specific name for it.
Okay, thanks.
Mhm. But I found it's very helpful to think about it in terms of not just I/O bandwidth as a umbrella term and not just compute bandwidth as another term. So thinking about it in terms of, okay, what is it the actual problem in my system can kind of help narrow down your search on what is the best algorithm, let's say. Okay. So my project at Los Alamos National Labs was titled A Virtual Cluster Monitoring Toolkit for Bottleneck Analysis. And my partner, Christian, unfortunately couldn't be here today, but he was very instrumental in this. And we worked together for, I guess, 3 months. I never met the guy, but we've worked 8 hours every day over Zoom. So he's very much a part of this. I will go over his parts. So when we talk about virtualization, basically we are looking at emulating one computer on top of another. And let's say, for example, you have a Linux workstation and you want to be able to run Mac software or Windows software or Android software. Using a virtual machine, you can basically simulate the same computer components, the same hardware, the same operating system on top of your Linux computer. What I worked on is called virtualized HPC clusters, where you have multiple virtual machines on top of your host operating system, and they are sort of packaged together in a infrastructure. So let's say you have a network, you have an internal network, you have an external network, you have infrastructure nodes, and you have shared file systems, everything that you can think of for an HPC cluster. The specific project that we work on is called HPC Collab, and it's basically a framework for designing virtual HPC clusters. It's open source, so if you are interested, I can definitely point you to that later. And the idea is that you basically specify a cluster recipe. Let's say you want 2 login nodes, 10 compute nodes, 1 gate node. You feed that into the HPC software, HPC Collab software, and then the output is a virtualized cluster on top of your host machine. So let's take a look at the different types of virtual nodes that we have worked on. So there is the file system node, the service node, build node, so on and so forth. And they each have dependency on the prior one. So when we talk about provisioning them, we have to first provision the file system, then the service node, then the build node, so on and so forth. And this process is actually surprisingly takes a long time. It takes about 2 hours for a 10-node cluster to boot up. And that is likely due to network bandwidth, other types of things. But the biggest question that we were tasked with over the summer was to figure out what was the monitoring, or to monitor it and figure out what was the issue, what was the bottleneck. And we started with these techniques that we talked about earlier, but to basically look at virtual disk read-write, virtual memory usage, as well as actual memory usage, CPU power, consumption, network performance, so on and so forth. And a special thing to note here is that a virtual machine does not act the same way as a traditional computer. It acts, some of the measurements are not reliable. We actually found out a lot later that things like I/O wait time are just not captured on a virtual hardware system. So how's the monitoring being done? Basically, we have a host machine and then all the different guest machines. And on the host machine, we start a monitoring script. So we have a main script that starts monitoring on that machine and then starts, basically initiates the provisioning process and starts booting up the nodes. And as each node is booted up, it has its own monitoring system that is gathering, collecting metrics there. Once it's done provisioning, then we have a sort of a collecting script. This is all done using Bash. We collect all the data from the host machine that we've collected as well as the guests. And we graph them. And then finally, we take all that data, we bring it to our personal workspace, and then we analyze the data and see what's useful. So when we first collected the data, it was in terms of a stream of text. So here's an example on the left of all the different interfaces from NetStat, and we graph them using GNU plot to show for example, here is the loopback interface. And what's interesting to note is throughout this provisioning timeline that we took, we saw different blips in increases in packet sent to over loopback, which corresponded to each of the different virtual nodes being started. So it seemed that the virtual interfaces that were being started or the virtual network interfaces were over loopback. So we took all this data and we converted it into a dashboard that has all the different interfaces as well as RAM usage, VM stat, and TCP, UDP, and IP segments. So this is the loopback interface we saw earlier. We also took into RAM into consideration, and when we look at the amount of memory that's free on the device, we see that at the beginning of provisioning, we have a large amount of free memory. The process before have let go of their memory and everything is free for a while, and then slowly over time we see an increase in RAM usage. And then here is an example of context switches as well as interrupts that happen per second for virtual memory, and we actually see that they increase a lot. Or we see, for example, for interrupts per second, we see different points where there's big spikes. And this is over a 2-hour period, so that's actually quite significant spikes. And they probably correspond to when the virtual node is first being brought up. And context switches we see increasing over time. So there is basically a hypothesis that as nodes are being provisioned, you have to go back to nodes that have already been provisioned and provide additional updates to them. So there may be issues that happen there with that. So another tool that we used this summer and we found extremely helpful was perf events. And it's essentially a fine-grained performance analysis tool. I'm sure people here who have worked with computers a lot, you've come across this tool. And there's something called flame graphs that we use in particular, which looks at the stack profile population on the x-axis and a call stack on the y. So note that stack profile population is not in terms of time, but rather in terms of percentage sampled. So things do not happen as you kind of intuitively think them. But on the, basically, what we learned here is that during the entire provisioning process, there was a lot of time that the CPU was idle. So this kind of goes into our hypothesis that the CPU or the application may or may not, or probably was not CPU bound. Yeah, sorry, this was the example of the idle time here that we see. So let's look at a case study for the build node, which is the node that compiles and builds all of the Slurm databases and different software for the rest of the nodes to use. And here's an example of RPMs being cached locally on the host versus them being fetched during runtime from a provider. And we see here that there's surprisingly not a huge difference between RPMs being cached locally and being not cached. So it seems that regardless of whether or not we've preloaded the RPMs on the host, there wasn't a big issue. However, this sort of visualization is useful in the terms of we look at increasing depth, increasing I guess it would be called a magnifying glass into the the packets or the interface that we're looking at. So Eno2 is the outward facing interface. That's the first column. And then if we dig a little bit deeper, we can see that the number of IP packets are largely coming from TCP. So that is kind of how you can traverse this. So some further directions for our project. We were hoping to add more functionality with perf and flame graphs into the automatic scripts that we created. That was not possible at the time being, but hopefully at some point we could also do that. And we also this summer found this really helpful tool called CollectD, which does these kind of visualizations for you. So in some ways we can kind of bridge the two to make it more kind of a cleaner code. And then we're looking at figuring out what is the overhead for virtualization and whether or not there could be potential speed up if we change the hypervisor platform. So right now we are using VirtualBox as our virtual machine hypervisor, but we also checked out libvirt, which is the open source Linux specific virtualization provider. We saw improvement, but another question would be looking at a third one and seeing whether or not the time to provision has really changed dramatically between them. Another interesting thing that we could look at is containerization. So the advantage of using a virtualized environment is that we simulate everything. We simulate the hardware, we simulate the operating system, everything for an HPC cluster. However, containerization really takes away the overhead of simulating everything. So you can kind of create faster spin-ups of HPC systems and model them that way. But at the drawback of you're looking at things from a user level perspective and not the full stack. Other issues that we were kind of thinking about were this HPC collab may not be scalable because we take 2 hours for a 10 cluster node. So having, let's say, 1,000 nodes, which is kind of a small supercomputer, would not be feasible, or at least in terms of time, if you're looking at quickly spinning up a cluster. And it also may not fit on one CPU or one computer. And that's because basically this is designed to be on one computer and not have a sort of a supercomputer simulated on top of a supercomputer. And then one thing that we have done is we've released the code, which is quite exciting. You can look on HPC Collab. And then we're hoping that other people can try this out and see if it works for them. Okay, that was my presentation for today. And here are some references. Brendan Gregg was the creator of Perf Events, and he has great resources for that. So if you're interested, I would highly recommend checking it out. All right, I'll look for questions. Feel free to ask anything. Singularity, I see. Cool.
I can give a plug for Singularity as well. Definitely use containers. Maybe that's the first step, and then and then try a few out and see what works in your case.
Great, yeah.
So forgive me because this sounds like a stupid question, but what did you in the end find was the biggest bottleneck, or is that still really an open question?
So it's still an open question. We have not really found the biggest issue. And that's mostly because of the fact that virtual clusters or virtual, I guess, nodes don't give you the actual data that you'd expect. So they don't, if you type in IO stat, they may give you garbage data. They may not be reliable. And so we kind of found this out halfway through our project. So we're kind of looking at, the next step is looking at what is reliable, what are the different things that we can count on, and what kind of can we infer from that. But one of the biggest issues that we think is like causing a lot of time, or I guess is the big culprit, is the overhead for virtualization providers. They are not necessarily, especially VirtualBox is not optimized for Linux, and that is likely a culprit.
Oh, there's a question in the chat. You can
Did
see
the
that.
vendor not recommend a particular monitoring package? Which vendor? In terms of monitoring packages.
So the HPC collab doesn't have any monitoring built into it, it sounds like.
No. So this is sort of I should clarify, this is a proof of concept test bed. So the idea with a virtual HPC cluster is that you spin one up, you test, let's say if you have security vulnerability issues on a bigger cluster, you can test them on this virtual cluster and not worry about compromising any other working clusters at the same time. You can also use this for educational purposes. So it really is in development right now. We don't have like, let's say Prometheus or other types of like storage for monitoring like that.
I had a question about the VM stuff, actually.
Yeah.
Do you expose metrics to the user? Like, for example, let's say I'm developing something on the KNL clusters and I want to collect some performance counters, right?
Mm-hmm.
Like, one of the things that I have had the biggest problem with on actual systems is that if it's a VM, there's no way you can run perf because all of those hardware counters require bare metal access. So like, how does it work for like traditional HPC deployments? Because it's kind of frustrating as a user to not have any way to like measure performance counters. Like, is there a way to get around it?
That makes a lot of sense. As far as the basic monitoring techniques, like you can use IO-stat, you can use these things. Perf, yeah, I think the problem is SC Linux. Like they, most of these things have SC Linux, and you can't really get much, like, they're not going to let you get anything deeper in, a deeper visibility into the hardware itself.
That sucks.
I can tell you there are some projects, they have to be supported by the site, obviously, but the site will monitor the metrics for every job that goes through the scheduler, and then the user can get that data after the fact, after their job has run. I don't know if that really gets you what you want. I know that one of the, I think TAC has a tool they're working on down in Texas.
Of course, it's gotta be McCaplin. Of course it. Why can't I just get sudo on my nodes?
Yeah.
Build your own HPC cluster.
That'd be the dream.
Why not?
A related question to that sense, is there a way to do anything bare metal? Like, I feel like for cloud HPC, it's like the biggest leg up, because if you could like spin up AWS bare metal instances and like do performance counters and stuff, like, is there a way something like that could happen for like on-prem or traditional HPC deployments? Like, is there a way forward? Can we get around this somehow?
Sorry, do you mind repeating? You mean in terms of like
just chopping the VM out? Like, you just don't want a VM. Like, could you do bare metal
for this kind of thing?
Yeah, for like a cluster, yeah.
The problem, yeah, I think the problem is the interconnect. Yeah. Mm-hmm.
Like, what are the challenges there in terms of the interconnect? I don't really know much about them, so I'm not sure.
So, okay, your question was in terms of, can we take the cluster environment, the virtualized cluster environment, and basically map that onto actual hardware?
Yeah, like just remove the virtual machine abstraction completely. Like, what if we just run it on the host OS itself? Like, would it be possible? Is that even a thing people do?
So that's basically the idea behind Pixie Boot. Like, you can take what's it called? Let's say an image and automatically like send it to a node, right?
Okay.
So you can sort of create whatever, if you have the hardware, you can create whatever sort of operating system and infrastructure on top of it using Pixie Boot, right? Using whatever downloader you have.
Okay.
So like our system, if you're asking about our system, yes, like we can basically take the monitoring framework, besides having the host node, so you'd have to sort of do some sort of juggling there, but you can basically get in like communication, everything. You can't add things like virtualized network interfaces. That may be a little bit more difficult.
Okay, I see. Oh.
If you want to take the complexity up a level, I know that OpenStack basically does this. There's an implementation of OpenStack called Ironic because it doesn't have VMs. It's just bare metal OpenStack. But so those tools give you great capability, but they're quite complex to set up, I know.
I'm not sure if I exactly answered your question today, but we can talk about it offline.
Yeah. I mean, that was still helpful because I know nothing in this area, so thanks.
As for bare metal, there is also more low-level provisioning services that offer like the security advantages and let people use them in that way. But I feel like the implementation needs to be a bit more low-level for the security purpose.
You mean that there are cloud instances that provide secure but bare metal?
Right. So you get bare metal hypervisors are more on a BIOS or firmware level, so that it becomes more secure. I don't know if any have been sold yet, but I do know that tech is like in progress because I've worked on projects with that.
The only one I know that offers that is AWS, because Nitro, like they develop their own BMC, so they can like just run the CPU by itself. But I don't think anyone else does.
Well, maybe that's all we have for questions. Thank you, Natasha. It was great to have you and see what you've been working on. This was certainly informative for me, so thank you.
Thank you very much. Thank you for having me. And yeah, hopefully I'll see you guys at some point in Boston when things clear up.
Oh, agreed.
So was this part of at Los Alamos? Was this a part of an internship there?
Yeah, so I had a Supercomputing Institute internship. So the first 3 weeks were a boot camp of how you design a supercomputer from the ground up. And after that, we had our own project. So about 2.5 months of a project.
Oh, that's great. No, I've had a couple of students there. It's a real great place. It's very unique. Very unique.
Was it in the HPC division?
Yep,
I'm assuming like parallel stuff, parallel architecture.
It was on the reliability folks with them.
Nice, very cool.
Doing beam testing on their system.
Interesting.
Yeah. Anyway, nice talk.
Thank you very much.
All right. Well, thanks again, everybody. We'll hope to see you soon, virtually, if not in person, someday soon.
Hopefully someday.
And Elliot, I'll be back to you soon with some other details.
All right. Sounds good. That'd be great. All right. Thanks, everybody. Have a great evening.
Thank you. Bye-bye.
Bye.